Hello. Thanks for joining. All right. Hopefully everyone's seen it at this point. Today I'm going to talk about blockchains. And we're going to dive into um, how they work, like how they're built technically, which actually they're not not too hard things to follow. We'll definitely start from simple foundations, and we'll work our way up. Um, uh, Before that, I guess I should actually give some just some standard things, which is thanks everyone for watching. Some of my Twitch videos have already started to age out of the Twitch archives. So based on the suggestion more than a few people made, I did go and make a YouTube channel that has the archive. So right now, anything that's not on Twitch, it's there on YouTube. And if you want to find the channel, it's the Shuffle Sharding channel on YouTube, or you can also go to my website, shufflesharding.com, and there's links to the YouTube channel there. If you just click on videos or whatever, should be pretty easy to find. So if you're looking for the older videos, that's where they are. Anyway, I'll cover that at the end. Anyway, today, like I said, we're going to talk about blockchains. And blockchains are pretty exciting, but also, can be confusing technology. There's plenty of things that are really cool about blockchains, and then there's plenty of things that are super controversial about blockchains. And my goal here isn't to get into, mudslinging or opinions about blockchains or in one direction or another. It's just just to go through it in a way where we can all hopefully at the end of this understand how blockchains work, right, and what the problems they solve are, and how and compare that to the history of those kinds of problems and how things go. So we're probably going to cover a few different things. We're going to cover what a ledger is, how transactions work, how distributed transactions work, some of the very basic pieces of cryptography that are involved in a blockchain, and things like proof of work schemes. And then we're going to glue all that together, and we're going to show how things like cryptocurrencies and NFTs work on top of that, and at least function at a technical level. And we'll see if we'll see what else we can get into as we go. If anyone has questions, just drop them right there. I'll either try to get to them as I see them, or I'll scan at the end as well anything I didn't answer, and try to get into everything. So blockchains. So I think the most important mental model to cultivate with blockchains, right, and the way to think about them is that blockchains are really a ledger or a registry, right? So if you think about blockchains in the abstract, right, what they are is it's kind of a immutable record that's actually being kept and cooperated on by all sorts of parties. The effect records transactions, right? You've got A sends money to B, say, or A does something with B, and C with D, and so on, right? At time X, and you've got all these transactions are recorded on the blockchain, right? In some kind of robust way that means these entries can't be undone, can't be spoofed, can't be forged, or anything like that. And if you're doing financial transactions on top of a blockchain like a cryptocurrency might, also that somebody can't just steal A's money or C's money or D's money or anything like that, right? That there's all sorts of security and authentication around that. But that model, that fundamental model, that like at its most abstract, or at least at one level of abstraction, a blockchain is like a list of transactions that have happened is pretty important, right? That's ultimately what it provides. And having a consistent list of transactions is actually kind of a famously hard, kind of old problem in computer science, or even predating, computer science, right? Here in the U.S., where I live, every night there's a company called DTCC, which is kind of a semi-public, semi-private company, which is kind of charted with every single night. It records the official record of like every stock or share transaction that happened that day, right? It gets it from all the trading houses and reconciles that and makes sure that there's no conflicts or double spending of money or anything like that. And everyone has agreed, that DTCC are the folks that do that. They're like the one entity that are allowed every night just like write down the list of transactions that actually occurred, right? And I don't know, but I presume it's very rare that they might find any errors, right? Because all of those folks who do the trading, the trading houses and so on, are hopefully pretty good at making sure they've kept their their records in order and everything is right and that stocks aren't being oversold and so on and so forth, right? But it's important that like record exists because people want to agree on who owns what, right? And the traditional people want to have especially for intangible resources, things that can't be physically held, whether that's an intellectual property or money that resides in a digital bank account. It's not like gold you can go physically touch in a safe or something like that. People want some party they trust to have the official record of what all that is. And that's and the traditional solution for that, right, has been essentially to nominate one party to do that, right? And I mean that like in a technical sense and in a political sense, right? Like governments and financial institutions generally have said, hey, DTCC, you're going to do it, right? And everyone agrees, and there's some regulation and oversight, and they do a good job of it, and our finance system can succeed, right? Now, in a technical side, an example of that is an awful lot of systems are built on top of a database, right? A lot of websites, a lot of web applications, they store their state just on a database, right? Like a SQL database or something like DynamoDB or whatever, right? And it's really common, you'll hear the term, there's a primary database, right? And maybe you've got secondaries or, failover databases too. But generally, right, to avoid inconsistencies, right, at any given time, like there's one primary database. Like for any given data set, there's like sometimes literally like one machine with one CPU somewhere that's responsible for like the actual recording and ordering of transactions and so on, right? So like in the database world, right? So let's say we've got a primary database and a secondary, right? Oops, gotta move my paper over a bit. I'll move my document camera. So when you're sending transactions, right? Like Colm buys, something from Bob, and then Bob buys something from Adam, and then Adam buys something from Lucy, right? Like something needs to reconcile that all of that's okay, right? Like something needs to check, wait, did Colm have enough money in his account? And now that money's in Bob's account and it's not in Colm's anymore, and so on. And all of those are transactions, right? And traditionally, we just like tried to route those transactions to essentially, one place for any given data set, right? And in the primary database world, or in the database world, we route those transactions to a primary, and it can, because it's one place, right, it can resolve conflicts relatively easily. It can say, well, since I'm only doing one thing at a time, I can quite easily say, well, I just checked how much money is in Colm's account. Now I'm going to spend it, and I'm going to decrement that money from Colm's account. I'm going to put it into Bob's account, all as like one atomic operation, a transaction, right? And it's important that all those things happen together. Otherwise, you'll get these weird inconsistencies in the system, or problems like Colm can spend more money than he really has, or things like that, right? And it's always been a hard problem to like distribute that, to have distributed transactions, because you've got all these sorts of problems. Like, so imagine if I have the simplest kind of distributed transaction might be a primary secondary system like we have here, where okay, well, I have a primary database for consistency reasons. I want to be able to have my transactions be robustly recorded without any conflicts, right? So that's why we don't just say, have like many primaries and pick one at random, and like sometimes your transaction will go here, and sometimes your transaction will go over here, and sometimes it'll go over here, or whatever. The reason is because, well, what if two of them try to spend my money at the same time, right? You're gonna get a conflict, right? So there needs to be something that's enforcing uniqueness and consistency, right? And that's why we try to route everything to the same primary. But a primary could fail, and we don't want to just have downtime then, right? We want to have something we could fail over to. So it's common to have a setup where we have a secondary, right? But even this really simple setup is still quite hard to do, right? It's like, well, if I've got a transaction that comes into my primary database, I can't just say yes to it, and then like after the fact send it to my secondary. That's a form of what's called asynchronous replication, but you probably can see straight away that that's not great, because if the primary failed like right after my transaction, and before that transaction had been replicated to the secondary would have no record of it, right? It's like my transaction never even happened. And if we had to flip over to the secondary, like the transaction never occurred, it's just gone, puff, right? So that's no good, that doesn't work, right? So you kind of go, okay, well, actually I'm going to send the transaction into the primary, and the primary is going to acknowledge it. It's going to say, okay, I've recorded this somewhere durably. We call that a journal, right? And then it's going to go to the secondary, and the secondary is going to go do the same, right? It's going to record it to a journal, and only then, when both of them have it, are we going to acknowledge the transaction and say it's good. And then we know it's stored in both places, and that's called chain replication. It's not quite a multi-phase commit protocol. Things like 2 or 3 phase commits. This is just chain replication, but it kind of works. The downside of this now is that if either the primary fails or if either the secondary fails, it's in trouble, and actually the system won't know what to do because it doesn't have 2 records of anything. And so you typically need a third system called a controller that can kind of coordinate things and say, well, look, if the primary fails, I'm going to make very sure it's dead. I'm going to really kill it in the head and make sure it's really totally dead, can't possibly come back. And then going to make the secondary the new solo primary, and it's just going to be able to carry on, but there won't be a gap, So it's pretty. You get robustness that way. So that's like a really simple version, right? A very simplified version of how like a simple distributed transaction might work. I probably already lost some people, but we will come back and re-simplify some of this later. So just from this primary secondary example, you can see straight away, okay, things are getting complicated. I have to think about what if messages get lost in this direction. I have to think about now I need a controller that can tell if anything is good. I have to be able to shoot things in the head really robustly and make sure they can't come back if I want, reliable durability in a system like this. There are generalized solutions to distributed transactions, including for more nodes than just this. And you get into things like consensus protocols, which I'll probably do a separate stream on sometime. But we have things like Paxos and Raft, which are distributed transaction or consensus protocols that they use. So let's say you've got 5 nodes, right? They've got proposal and voting rounds and all sorts of things I'm not going to get into right now that help them work. But essentially, they try to make sure a transaction is recorded durably by saying, well, as long as a majority agree on what a transaction is, that's when we're good. That's when we know a transaction occurred, and can't ever be changed or anything like that, right? So like, let's say this guy gets it, this guy gets it, this guy gets it. Now the transaction's real, right? Because 3 out of 5 have it. It's a little more complicated than that, but that's essentially it, right? And eventually they all get it, and the transaction is robustly recorded. That's just a really dumb example of a majority-based consensus, but like, have that mental model. We'll need to pull it back in a bit. So, and then to extend this a little bit more, so let's say we've got an arbitrary number of nodes, right? In a system like these primaries and secondaries, or even a system that uses Paxos and or Raft or something like that, in general, like all of the nodes, all of the participants in these systems tend to have to agree about each other's role, right? Like when you fire up this system, the controller kind of has to nominate and say, well, this guy's the primary at this particular point, right? And this guy's the secondary. In a Paxos or a Raft system, you'll typically elect a leader, and everybody kind of agrees who the leader is. That can be like really simple and deterministic, like, we're just going to pick the first guy to be the leader, or excuse me, or it can do something like dice rolling, right? Like it can have every single node roll a dice, and whoever gets the highest number wins. And if 2 or 3 nodes tie, they just go again until you get one clear winner, and that's how you pick the leader, right? And so on. A hard problem that you have to think about in these systems is partitions. It's like, okay, well, I've got my nodes. Well, like, what happens if, the 2 nodes on the left lose visibility of the other 3 nodes, right? And vice versa. Well, if you get a nice clean partition like that, things are quite easy. The 2 can see, well, we're in the minority, so we should just refuse to serve any transactions. We can't possibly keep going. If we're in the majority, we can keep going because we still have a majority, right? So we can still operate. There are other evil kinds of partitions where, like, these 2 can lose visibility of these 3, but these 3 can still see those 2, and so on. And then that's why protocols like Paxos and Raft get more complicated and have to include, proposal and eligibility and voting rounds, and make sure that nodes really can acknowledge and see each other's things, and so on. The most important thing to take away from everything we've covered so far, right? It's just this foundational concept that what a blockchain is a kind of record of transactions, and that doing transactions, traditionally, it's a pretty hard problem in computer science. In general, we've solved it by routing transactions to like a single node somehow that can just record those transactions and make sure that they're all conflict free. And when we've had to do things in a distributed way, like using lots of nodes, things get complicated, and we have to use distributed consensus protocols, and so on and so forth. And what's kind of really cool about blockchain, at a technical level at least, is it came up with a solution for doing distributed transactions that's pretty nifty, that is robust against some kinds of interference, right? So both this database example and like a Paxos or Raft example, like these nodes have to be cooperating. If you've got a malicious node, right, that's really trying to mess with the system or lie or interfere, like I don't think you could make those systems work. Like it's just not really doable. So if you were trying to run this as like a fully peer-to-peer system where like just anybody can run their node, it's not really going to happen. But at the core of blockchains, it kind of is a solution for that. And I'll go through how that works and how blockchains were able to kind of resolve that dilemma. So To understand blockchains, we're going to need to understand how they work, right? Not just what they are. We're going to need to follow two cryptographic concepts that are pretty indispensable. One is hashing, and the other is asymmetric signatures. And I'm just going to very briefly explain both, right? So hashing, I've explained before, but I'm going to try and take a better run at it because there's some properties that really matter for us here that I haven't covered before. So examples of hashing algorithms are things like MD5 or SHA-256. And I'll just use SHA-256 as a simple example, right? But SHA-256 is a function, right? And it takes any input you want. So we can put a string in here. Let's say hello world, right? And that's the input, and it produces a 256-bit long output, right? So if we were writing this in binary, there'd be, I don't know what it would be, but it'd be, and I'm just making these numbers up just to be clear, but we do that and we get 256 of these bits, right? So, and there's some important properties. Firstly, it always emits 256 bits, no matter what, right? It's important that, if we run the same string twice, we'll always get the same result, right? So no matter how many times I run SHA-256 on hello world, it'll always come out with the same answer, every single time. It's deterministic like that. And two independent parties can run this with the same input, and they'll get the same output, right? No matter what. So it's very, very easy to verify, given an input and an output, that they correlate. Trivial, like milliseconds, microseconds work, right? So that's important. Another thing that's important is if I changed even one bit of this thing over here, even just one bit, right? This output would change dramatically, right? Like a 1-bit change over here, let's say changing this E to an F, right? So if I did the same, but it's like that, which I think is a 1-bit change. If not, it's a 2-bit change or something like that. That's not going to resemble this original output at all. It's going to be completely different. In fact, for every single bit, it's got a 50-50 chance of being the same or not, right? So maybe that one's different. Maybe that one's the same. Maybe that one's the same. Maybe that one's different. Maybe that one's different, and so on. But there's just like no correlation. Even it's a 2-bit difference. There we go. But even the slightest change in bits over here dramatically changes the output. There's just no correlation between them. And then another thing that's interesting, as an aside, this is totally unpredictable for what it's worth. And another thing that's interesting as an aside, now obviously there are only 2 to the 256 potential outputs here. Only, I said in quotes, like that's not an unbelievably large number. But there's obviously an infinite set of inputs, right? So in theory, there clearly are inputs that will collide, right, and produce the same output. We call those collisions, right? Now in the real world, we expect a hash function to be uniform in how it produces these outputs, and 2 to the 256 is a huge number. In fact, I think it's more than there are elemental particles in the universe, in the known observable universe, right? I think it's actually even more than like the potential combination of elemental particles in the universe. Like it's a really, really big number. So, so the reality is it's probably vastly fewer real-world inputs than outputs. And collisions aren't something we should have to worry about, and actually when hash functions are found to be broken, often it's that, actually we found a shortcut in the algorithm, that let us find collisions, which is bad, right? So that's what hashing does. We're going to need that primitive, and we're gonna come back to that for 2 different purposes as we go through our example blockchain. And then the other thing we need to cover is public and private keys and asymmetric signatures, right? So these are actually pretty simple. So we're not going to get into the math of them at all, but basically you can create a public and private key pair. In blockchains, these tend to be elliptic curve based keys, so they're nice and small and fast, right? But you create a public and private key, you can give that away, right? You can make your public key public, and then the important thing is you can sign things with your private key, right? So you can sign something with your private key, and anybody who sees the public key can check that you and only you, or at least only somebody with the private key, could possibly have signed that, right? So that's pretty important. All right, so those are the only two cryptographic concepts we're going to need, right? There's actually a bit more distributed systems in here than cryptography, but we'll try to glue it all together. So I said earlier that a blockchain was basically just a record of transactions, right? Now in the banking world, they've been calling that a ledger, right, for a long, long time, right? Ledgers are, they're like a bookkeeping thing, right? You've got this transaction followed by this transaction, right? So that's what a ledger is. And when you create, let's say we're building a cryptocurrency on top of a blockchain. When you create a wallet, right? When you create a blockchain wallet, or you want to participate in the blockchain, you create one of those public-private key pairs, right? That we talked about, right? And in this ledger, right? The transactions are signed by the parties, right? So when we see a transaction that's like, well, A is giving money to B, right? That's signed by A with a signature from A's private key, right? And then, later, so there's some more transactions, and then let's say B sends money to D, just to be different. That's signed by B's key, and so on, right? And there's not really too much more those individual transactions than this, right? It's like, A had money in their account, and we'll get to how we tell that in a second. And then they sign some transaction with their private key, and we put that transaction on the ledger, and now B has that money, right? And anybody who can read this ledger can see this happen, right? And if you have a ledger that goes back to the beginning of time, right, and basically like the invention of money in this system, just by kind of reading every transaction in this system in order, you can figure out, how much money is in anybody's given account, right? You can we'll talk later about how that money gets there in the first place, but you can kind of see about, okay, well, let's say I know at some point in time A has like $100 in his account, and then I see a transaction that's like, well, A now gives $20 to B. Well, I can say B has $20 more than they started with, and A has $20 fewer than they started with. Easy, right? And then I go through this ledger in order, and as long as those rules aren't being broken, it's really, really straightforward to follow. Now, in the traditional world of like centralized finance and banking and so on, this is done by banks and clearinghouses and like the DTCCs of this world, like I mentioned earlier, right? They are responsible, like the clearinghouse and your banks, like the banks at the parties, are responsible for saying, okay, well, the clearinghouse gets this transaction. A wants to send $20 to B. Well, it asks A's bank, do they have $20? And sends it, if they do, deposits it in B's account, removes it from A's account, and so on. Those systems don't have perfect consistency, right? And that's why you have things like overdrafts, right? Sometimes, sometimes you do have multiple transactions in flight with different clearinghouses, and they're not perfectly coordinating with one another. and so they might simultaneously clear transactions, even though it gets you beyond like how much money was in your account, and then you go into overdraft and so on, right? But they have limits on that. You know, they'll do that for like $100, but they won't do it for $10,000, right? You know, for $10,000, they'll do a different kind of transaction where they basically lock your account for a bit, don't let anything else happen. You know, do the $10,000, unlock your account, right? So that you can't get two $10,000 mistakes at the same time, right? But like that's how it works, right? And those clearinghouses and banks and so on, you know, they're regulated by governments, and if they screw up, you can have the regulators chase them or sue them, or you know, there's systems of laws and governance and topics I'm not an expert on that, you know, help you have some confidence in that system, right? But that's what gives them the authority, right? Generally, the mutual agreement or the force of law, right? And sometimes, you know, parties can keep this stuff in house. You know, if A and B share the same bank, then maybe this transaction never goes to a clearinghouse. The bank can just do it internally, right? Or like two people on PayPal sending one another money, right? Doesn't have to leave PayPal at any point, right? Another kind of simple example. So, but in blockchains, one thing that's a little different from like just your regular bank transaction is the individual transactions are signed by your private key, which is good. In fact, I think this is one of the best things about blockchains. This is awesome. I wish we had this in like regular banking. And therefore you can see this transaction was definitely signed by someone who had A's key. All right, so straight away you can see, well, if I keep a ledger or a record of like every transaction since the dawn of time, that's gonna get pretty big, right? That's gonna get pretty long and pretty big. And so there's a few compression techniques, a few things you can do to try to solve this. One is sharding. That's actually quite hard. I'm not going to get into that too much. But the more interesting part is kind of the block part of how blockchaining works and what blockchaining really is, right? And that's if we deconstruct this whole ledger into a series of blocks, right? And we say, okay, well, all the transactions in a certain time window, you know, end up in this block, or a certain size limit, whichever they hit first, right? Either the time limit or the size window, you know, and they go in this block, right? But what I can do at the end of the block is I can say, well, for all these transactions that are in the block, I'm going to run a hash over those transactions, and that's going to produce a checksum or a digest, which going back here, that's like this part on the right hand side, the output of a SHA-256 operation, right? And so this is going to get like a checksum or a digest that now represents the entire block, right? If anything in that block were different, this would be different, right? So this little checksum fully represents everything that's kind of in that block, right? And then the next block that comes after, it's going to have the next transactions, blah 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 blah, right? And it's going to have a checksum, right? But these checksums, right? Instead of this checksum being like everything since the dawn of time, right? It's just going to be everything in this block plus the previous checksum, right? So in order to validate everything that's in this block and agree that it's part of the overall ledger, right? You just kind of need to start at some point where you go, okay, well, I agree that this was the checksum of the ledger at this point in time. But you just need to check if everything forward from there to like where the transaction you want to validate is, right? This is how you can check a chain of transactions without ever having to check every single one. I'll try explaining that again because I probably didn't do too good a job. It is like a linked list pointer. So it's the job here is, right, we're going to get to consensus in a minute and about how everybody agrees on this ledger and how that part of blockchain works. But we're going to for the moment, the thing is, to validate the ledger, we don't want to have to validate the entire ledger every single time from the dawn of time, right? That's just too expensive. So what we want to do instead is say, well, if we can get everybody to agree, look, this was the tip of the ledger at some point in time. It had this known hash value, right? Well, then they can very cheaply validate all transactions from then on, right? They can see that the next block, depends on that hash, and so on, right? So that's the next important property. Now, if they still want to recompute the value in everybody's account or whatever, they still kind of have to replay absolutely everything. Now you can have summarizations at different points. Like you can insert records on the ledger that say the current value in A's account is $120, right? And if that ends up being signed and put on that part of the blockchain, you can trust it. And we'll see now what the theory of trust is. How these blocks can be generated. So blockchains, let's take a cryptocurrency example. They're peer-to-peer systems, right? So absolutely anybody can just fire up a node and it'll participate in this mesh, right? Where all the nodes can see all the other nodes. It's not like a completely full mesh. It's not like every single node is literally talking to every single other node. There's summarization protocols and so on that drastically simplify a bunch of the communication. But essentially, it's an open node system, right? Like I could go spin up something that participates in the blockchain, right? And those things are miners, right? Or they're doing mining, right? And the reason it's called mining, right, is because in addition to sharing the ledger and the transactions that are on the ledger, these nodes are also trying to mine new cryptocurrency tokens. So let's say new Bitcoins or whatever, right? And it's this active mining that is simultaneously probably one of the most controversial aspects of blockchains, and we'll cover why, and also the most magical part of it. It's how they solved that distributed transaction problem before, right? So imagine, right, we've got our ledger, right, and we've got our signed operations, and we're saying, okay, let's say I'm A and I want to send money to B, right? The way things work in a blockchain is, well, I propose that transaction, and I just kind of put it into the blockchain network and say, well, this is a transaction I would like to occur, please. Neither me nor B can consider that transaction complete until it's been recorded on the blockchain, right? Till it's actually gone into the next signed block, right? That's when I know the transaction is complete. So there's this window where I've proposed it, but it's not yet recorded. And what's happening in that window is, right, for all of the floating transactions that are just kind of there pending, full final commitment or whatever, is every single node in this network is kind of having a little race to figure out who can commit it first, right? And if they win that race, they get a prize, right? They get a token, right? This is how money is also generated originally in the system, right? And so they're incented to actually be doing some work to win that race because they get that prize, right? And they're also, they can only win the prize if everybody else, or at least a majority, agrees that they won the prize, right? Now, everybody else isn't going to agree they won the prize if they're breaking the rules, right? So if they don't record the transactions faithfully, like if they change my $20 to $21, these other nodes are going to go, well, that's not a faithful recording of what we think is pending. So you didn't win the race. Get out of here, right? You don't get a prize, right? So that's how they're all incented to record the same thing, right? Or to try to record the same thing. It's that prize, and you can only win that prize if you do things correctly, right? And it's important that they have this incentive, because actually winning the prize itself is kind of costly, right? It costs resources to do it. In fact, there's different schemes. Different blockchain networks have, some of them use proof of work, like Bitcoin. Some of them use proof of space, like Chia, where they're proving that you've got a certain amount of memory. Some now are trying to move to proof of stake, which I might get back to later. But let's cover a really simple proof of work scheme to see what's going on, right? So remember earlier when I said, okay, well, look, if we change any bit or 2 bits of this, we're going to get a really unpredictable output here, right? We just have absolutely no way of knowing what this output's going to be, right? So a really simple proof of work scheme, which is actually used by some blockchains, is to say, well, the way you can win the race is, okay, well, the block that you're all competing to kind of sign is it obviously contains the pending transactions. Those have to be in there, right? But let's also have it include just a little random parameter, just a little bit of randomness, right? Which everyone can see, right? And now adjusting that piece of randomness is going to completely change the hash, right? It's going to completely change the hash value. So what happens if we make a little game that says, okay, well, the way you're going to win the race is you're only going to win the race if, let's say, the first 8 bits of your checksum are all zeros, right? Well, to do that, because there's no relationship between the input and the output, you're just going to have to try a lot of inputs, right? And so to find an input that produces all zeros as that output, just for the first 8 bits, you're probably going to have to try, like, I think it's 256 inputs, right? 2 to the 8. You're going to have to try 256 different things until you probably get one that is all zeros for the first 8 bits. But the second you do, right, you can just publish that block to the network, and everyone in the network's going to see, well, your block has the transactions we recognize in it. They're faithfully recorded, and that hash matches. So the piece of because we can all check that. So the piece of randomness you came up with is the right input to generate something that has the first 8 bits of 0. Great, you win the race, right? Now in reality, it's a lot more work, and this scales, exponentially badly for you, right? Like if you need the first 9 or 10 or 11 or 12 bits, it gets twice as hard every single time, and very quickly takes an awful lot of work, right? So what these miners are doing, right, is they're just constantly spinning, trying new inputs until they can win the race. They're hoping to be first to find that random number that will produce a block that has whatever the current difficulty factor in the network is, right? Whatever the number of bits we've picked is, and then wins the race. And then everybody's agreed, like, if you win the race, we also credit you a token, right? We give you a Bitcoin, right? And so the miners go, yay, I won, I've got my token, and also this block is now recorded on the network, right? And this is kind of magic, right? This is like, in traditional distributed transactions, right? We could never really guard against malicious actors, right? Because they didn't, like, a malicious actor sometimes has a strong incentive to lie, right? Like they maybe want to pretend they have more money or credit somebody with the wrong amount of money or something like that. But in this system, because everybody has to agree about what the transactions are and who the winner is, it's kind of a fair game, right? Now, not to pass too much of the controversy, but like the big downside of this, of course, is now you've got a collection of miners each doing a huge amount of throwaway work, right? Even the node who won the race had to do a huge number of computations to win the race for that one block, right? Like that machine was probably running 100% CPU or using these special crypto mining pieces of silicon, consuming electricity, really going at it to just win that little race, right? And all the other nodes, and there can be millions, they just throw away their attempts. They didn't win the race. And they got to move on to the next block now, So they just got to accept defeat and move on. So this is staggeringly wasteful, right? Just huge amounts of energy being expended to win that race. It also interestingly kind of bounds, if the prize of the token isn't worth more than the amortized capital costs of that equipment and the electrical costs and so on, the operational costs, it's not even really worth winning. It's not even really worth playing this game. So like feasible blockchains, tend to have to be, they have to be both. They have to be a few things at the same time, right? They have to be big, because the second any one party can take over 50% of this network, all the security goes away. Somebody can just game this. This is called a Sybil attack, but somebody can just game this, and they can decide not to enforce the rules anymore, and they can just say, well, we're the majority, so screw the rest of you, and we're going on. So you generally need a big network which doesn't have any clear majority participant who could just game the system, right? So that's one important property you need. Second important property you need is that the value of the new tokens that are minted has to be worth doing the mining, has to be worth playing this game. If it's not, you're not going to get miners, right? And it's not going to succeed. So you probably can't just have like an infinite number of blockchains, or even probably a very large number of blockchains, right? Because the incentives for the miners stop succeeding at that point. So you need critical mass for that too, right? So those are pretty important considerations. So that's what's going on, right? Now, this is it's a pretty cool, nerdy thing in terms of a great way to solve distributed transactions, right? Wow, we figured out a way for this, cooperating system of anybody who shows up to actually agree to reach a consensus value on how to record a transaction. There's some other downsides. So as I said at the very beginning, this is just a ledger, right? We're just recording this series of blocks, right? Oop, sorry. We're just recording this series of blocks, right? So if you want to find the actual value in somebody's account, you got to replay the entire ledger and track every single transaction and figure out what was there. And you need other parties to do that. It's an incredibly inefficient data structure if you just want to know what the current state of things are, right? Summarization can help, like I said earlier, which some blockchains have. So periodically they can just inject these summaries that are like, here's what the entire network agrees is the current value of A's bank account and so on. So that kind of gives you these point-in-time snapshots, which you can get going from a bit sooner. But it's still, it's not the most efficient way to look something up, right? It just gives you this register. The other downside of it is it's slow. Very, very, very slow, right? So when you do a primary database setup, the reason why you're electing a single primary database to record your transactions is because it can do it in sub-milliseconds sometimes, right? It can be yeah, this transaction came in, I made sure there's no conflicts, recorded in my journal, done, right? All happening in one place, all happening on one machine. In the blockchain network, right, we're having to propose the transaction for tens of minutes often, right, where it's just floating out there, may or may not ultimately get recorded. There's reasons why your transaction might not make it into the next block because maybe not everybody saw it in time, and then you got to figure that out and retry and so on, and so that introduces some inconvenience. And you tend to have have to have other parties kind of counter manage that for you. And so the but the actual chaining stuff, like that's pretty cool. And this is a pretty standard technique, right? Like you can do this in audit trails or things like our QLDB, our database, where you can have a cryptographically signed chain of like this occurred after this, after this, after this. That's really, really robust. That is a very easy, efficient way to prevent somebody from going back and ever tampering anything or forging history. So that's very useful on its own. But this network part, has significant downsides. Now, we've more or less covered difficulties there. Where did I disappear? I think I was talking about immutability, right? Sorry. All right, let me roll back. So I think I was talking about this when things cut out. Still nothing. Oh man. So I think I was talking about how hash chains on blocks, right? So if we have a block here and it's got a hash at the end, and then we chain it to another block, that is a nice, convenient way to kind of build systems that you can, at any point in time, kind of have confidence that nothing was edited in its history, right? And this is something that audit trails have, some audit trails, and it's something that like our own QLDB has, which you can just build in a database. And I think I said already, I think this is probably one of the coolest, most awesome things about blockchains. All right. So hopefully, I'm going to check the chat. So I think hopefully you all got how the game works here in terms of how mining succeeds. Can anyone confirm whether they got that part? Which essentially got that. All right, good. So there's a few important properties here, right, that these nodes all have to do, right? One important property is that they're enforcing the same rules, right? That they can all agree about what the rules are. And there's some just simple examples of what those rules can be. Like, so the most simplest and obvious for a cryptocurrency is just saying, okay, well, A can transfer money to B, but only if he has that money in his account, right? Or C can transfer money to D, but only if she has that money in her account, right? And it's very, very simple rule to enforce, and it just requires them tracking, well, how much money is in each account, and then letting the transactions through or not, right? And that's an example of how these fungible tokens are done on top of a blockchain network. But the rule can also be for non-fungible tokens, right? So that's what NFTs are. And so the rule could be, A bought this digital picture, right? And the ledger will record, yep, A owns this digital picture, and they can sell it later, but only they can sell it, and they can only sell that picture, right? So that's what we mean by it's not a fungible thing, right? It's the ownership of that digital item that they're conveying, right? And that's really all NFTs are. It's just like using the blockchain as a title registry, so as this robust record of who owns what, right? And I'll come back a bit into what the true nature of ownership there is, but we'll accept that for now. And then another thing a blockchain network can do is smart contracts, right? So you could have rules in your transactions that are like, I promise, A promises to give $50 to B if party C, and let's say that's the U.S. Geological Survey, agrees that there was an earthquake, right? So let's say it was an insurance contract, right? Well, since the rule is recorded on the chain there for everybody to see, the nodes can just go execute that rule autonomously, right? If that third party, like the USGS, which is sometimes called an oracle, says, hey, there was an earthquake, then party A's money automatically goes to party B, right? It just happens. Neither party A nor party B have to do anything. The nodes just go execute that, and this thing becomes kind of like a computer, right? And so in that sense, you know, the rules can be as complicated as you like, but you do have to get everybody to agree on the rules, right? So, and since you need a lot of nodes in the first place to build a successful blockchain system, you know, that can't just be hit with those 51% attacks and so on. You got to convince everybody to update and, you know, implement those rules and so on, which can be its own challenge, right? So that's what's going on technically. There's really not too much more to it than that, right? It's just a distributed record of transactions. The main advantages are it's a peer-to-peer consensus-driven system. Anyone can participate. There's this nice incentive-driven system that kind of encourages people to mine and keep the system honest. And it's pretty cool like that. The downsides are it's incredibly wasteful of energy or space or whatever in terms of a proof scheme. Although I didn't mention proof of stake, I'll come back to that. And it's incredibly wasteful, or it's incredibly slow. It's pretty slow to record transactions. But it does, as long as you trust it and you trust all these people to be playing fair and you trust the nature of incentives and people to enforce those incentives and the purity of the game, you know, you do get a pretty strong cryptographic record of who did what and how, and it's kind of independent, right? So I said I'd talk about proof of stake. So proof of work schemes we covered with the hashing example. Proof of memory is pretty simple. It's just another kind of smart cryptography that instead of proving you've got CPU cycles, lets you prove you've got lots of memory. In my opinion, not much more environmentally beneficial. I mean, the cost of memory, the environmental cost of memory and storage and so on is also quite large, right? And in fact, requires physically mining precious metals and so on more than CPUs contain. So it might even be worse for the environment than just spinning a lot of CPU. Proof of stake takes a different approach where instead of wasting all this CPU to compute a hash value or waste a lot of memory, it instead lets you use tokens you have and the keys associated with them to prove, well, I'm sitting on this pile of tokens, so that's going to be my proof that I'm eligible to win this race and win this game and so on, which is kind of less gameable, but it also kind of goes back to square one, I think, in kind of economics, and that it kind of rewards the parties who have the biggest stake, which is like, you know, philosophically maybe one of the original goals cryptocurrencies were trying to avoid, right? That it would be a fairer, flatter system. And from there, let's talk about something I'm actually not an expert in. So I left this to the last part because I think it's important to cover and talk about how it interacts with blockchain, which is money supply and monetary supply. But I am not an economist. And I'm going to give you my best take based on reading books and articles and all that kind of thing. But feel free to educate me. Well, feel free to educate me about anything, but like especially this. And maybe think about it more as a series of questions than more as a series of answers when it comes to this. But it seems to me, you know, blockchains are exciting, right? There's some coolness to them, and people seem inspired by them, that they're capable of changing some things that, you know, weren't as easily changed as before. And at the same time, then there's other folks who say, well, but also, well, cryptocurrencies especially, they're just a scam or a pyramid scheme, right? And I think both things can be true at the same time. And trying to understand the difference, I think, is interesting, right? And trying to see what's going on. And it's the way I think about it is kind of like this, right? Let's ignore blockchains for a second, and let's just think about regular money, right? Which we're all pretty familiar with, and how that came to be, right? And it's like, you know, if you, for millennia, right, as like people evolved, right, and as we went from being hunter gatherers to industrialized societies, right, we had several kinds of value, right, that we had to interchange, right, like we had basically, like, if you think of, we were all kind of we all kind of started with, like, well, the resources that are like literally in, like, the planet, right? So this is my elementary picture of Earth, right? It's like the physical resources that are in the planet, and like the energy resources that come in from the sun, right? And that's that's the starting point of what's actually there, right? And we would hunt and gather resources from the planet. We would hunt animals, or gather berries or fruit or whatever we want, right? And the economy was driven by that. And so some people would do labor, right? They would go out and they would actually find those things, and they would bring them back to the community, and everybody would get to eat. And there was certainly some kind of interchange of value there. Maybe other people were doing other kinds of labor, like child minding or educating, and so on, right? But very simple, rudimentary economy, and you can see how people just exchanged, in some form, stuff that was coming from the earth for less tangible kinds of things like labor, right? And then economies advance. At some point, other things become valuable. You might agree to give somebody, a batch of fruit for composing a poem or writing a song, right? It's a completely intellectual exercise, but you still recognize that it has value, and you're willing to give something for it, right? And this, as societies evolve and they start farming and so on, and then eventually when they industrialize, you get more and more sophisticated goods, and just exchanging one thing for another, like bartering and sharing, like, it just stops working at some point, right? And you just, to keep things going, you need to have some kind of currency. It's just much more efficient all around. And independently, several cultures all over the world converged on, we should produce shiny little metal things, right? Because and they would go, well, we're going to say these shiny little metal things have a certain value, and we're all good, right? Like, we can use that as our common interchange format, right? And that's what currency originally was. And everyone kind of can have an easy time having faith in that and believing it, because shiny metal is actually hard to procure. It takes a lot of labor and organization to mine something like silver or gold, right? It's not something anyone just randomly go do. Although the gold rush in the US is an interesting counterexample of that, right? And just like become richer overnight. So you perceive that it's a very stable thing, right? And it's nice and portable. It's easy to keep clean. It's got all those super advantages. So everyone converges and says, okay, we'll just use these shiny metal things. And then at some point, the economies grow much faster than the rate at which you can really mine for shiny metal, right? So and the economy can grow in all sorts of ways, right? Like composing poems or songs, that has no bounds on the physical world, right? Or all sorts of labor, or more sophisticated endeavors and so on. They don't have to be fundamentally constrained by the resources of the earth, or how much gold is in there or whatever, right? So then they get the fractional reserves, and they say, okay, well, we can't get enough gold or silver to match the rate of the economy growing, so we're going to say instead that we're going to start printing it on paper, but you can turn the paper back into shiny metal, and so that everybody believes in the paper, right? And then but not everybody's going to want to do that at the same time, so any given country or any given printer of that paper, they only have to keep 10% of the value in gold or whatever, right? And then we used to do that for a long time, right? But people believe in the paper because they think if they had to, well, they could go get gold, and they believe in gold because it came from the ground and so on, right? And then at some point, in the 60s, these governments go, keeping all this gold around is pretty dumb. People believe in this paper, and we don't need to convince them of that anymore. And in fact, we don't even need the paper sometimes. We can just do all this in computers and accounting and bookkeeping because we know how to do that now too. So we're just gonna have a fiat model, right? And we're just gonna say the money's worth X, and that's that. And in fact, we'll also allow ourselves to print money, and which continues to this day. Things like quantitative easing and so on. But this allows the money supply to kind of match economic growth, and maybe it fuels economic growth, right? There's like a two-way relationship here, right? And printing money is an interesting philosophical exercise. It's not like when they print money that the governments just give it to themselves, though they could. And it's also not like they just give it to everybody in the country. Why not just give everybody a few dollars each or whatever? And that would be a way to match the economic growth and so on. What they've mostly converged on doing is, okay, well, we've got Federal Reserves and they print money and they credit it to banks, who in turn can loan out that money, and hopefully they do it in ways that are economically advantageous, and that's an important role, and that they're stimulating the economy in the right way and generating, growing the overall economy in advantageous ways. And people have or some people have a bunch of problems with that, right? And they see that, it can be a bit of a rigged system. It seems unfair. Maybe that governments can just print more money if they want, or allow more money to be printed if they want. It seems unfair that, some elite set of banks gets to be first in line for that, and just they seem to have these, guaranteed business models that just inure them to, having to do a good job or whatever. It could seem unfair maybe that we don't just give everybody $5 each or whatever it would be every time we print money, right? All sorts of things about it. It's also, the crashes earlier this century where, certain banks, certain financial institutions were too big to fail, and government stepped in and, basically, rescued them and so on. Also seems like there's a bit of a rigged system there, right? And that things aren't great. And people, I don't know enough to take a position on those things, but I can definitely see where people are coming from, right? And then they see, well, blockchains don't have any of these problems, in air quotes, right? A blockchain is just a completely fair system. It is a emotionless, unpolitical collection of robots just executing the rules that everybody has agreed in advance, right? And it can't be corrupted, right? And so we'll have greater fairness and stability over time is the kind of pro argument, right? That but the downside of it is this game that we mentioned at the beginning, right? That miners are only going to participate when they can believe they've got a pretty decent chance of winning the race to get new tokens, to basically print new money. They get to print new money at a profitable rate, right? So that each miner has to win that race often enough for it to be worth their while playing, right? And so fundamentally, that makes the price, that kind of limits the inflation or deflation of tokens that can sustain a blockchain network, right? If you see massive deflation in the price of tokens, if it goes way, 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 way down, and you don't think it's likely to rise much again or go up, the miners are just gonna leave, right? Because they're not, the token's not going to be worth it anymore, right? And likewise, the miners, the tokens that they have, the ones that they've mined, especially in the past when mining was cheaper because there were fewer participants, right? They're strongly incentivized to have the price of tokens increase, right? So they want more and more miners to participate so that the price goes up, so that the kind of bank of tokens that they're sitting on increases in value, right? And and that does strongly resemble a pyramid scheme, right? Or a multi-level marketing thing, right? Where like the early participants who got in there super early and could mine bitcoins at a certain price or mine tokens at a certain price. Sorry, you know, they really want some more folks to come along, so it increases the price of mining or of the tokens, and then they can sell them, right? And they'll do so at a higher profit. But the downside is the new miners never really get to make that profit, right? And the overall kind of economic growth in the system, right? The overall amount of tokens is pretty severely moderated by like this complex game of like how willing new miners are to enter, right? And grow the overall rate at which tokens are being mined. And it seems to be a pretty conservative rate, like in comparison to like what we've had to do to grow the global economy using regular money and fiat currencies and governments. Like it seems pretty severely limited. And if you were to imagine the like world were to just run on some cryptocurrencies, it doesn't seem like the math would completely work out. You know, it doesn't seem like what's being generated in those cryptocurrencies would keep up or with overall economic growth, and would probably moderate overall economic growth, which is not a good thing, you know. And this is all tied to, you know, people are dissatisfied and unhappy with all sorts of aspects of the financial system or inequity, right? Like, you know, some people can make far more money than others, including people who are doing it from just simple appreciating assets. All right, some things I forgot to mention. Hopefully, based on how we covered blockchain, some things should be clear, right? Which is that since it is this just distributed ledger, right, that everybody can see and everybody can agree on, there's essentially there's no privacy of transactions in this system, right? Everything's happening in public on this blockchain. You know, you see the key IDs, that it's not like there'll be a physical name attached to that. So there is a little bit of privacy in that sense, but you see, you know, the owner of this key is transferring money to the owner of this key, and so on and so forth, right? And in general, in systems that are that public, it's pretty easy to figure out who's who. You know, we're pretty good at figuring out patterns and so on. So there's just no real terribly meaning privacy of transactions in here, unlike the regular banking system where everything is, you know, pretty private, and maybe, you know, governments and so on might have access, or regulators or law investigators, but in general, I don't know what, you know, my neighbor is spending, right? Blockchains don't work like that. Now, of course, you could do a lot of transactions off the blockchain. They could happen inside the clearinghouses, but at that point, you're not really using a blockchain, right? So that's one thing that's not there. Another thing you notice, I mean, you know, people see blockchains as an investment opportunity, but if you believe that, you got to believe that that they're going to appreciate in price, right? Which is essentially equivalent to saying, well, the rate of mining is also going to increase, and we're going to go and see even more and more miners, and it's, you know, kind of like tulips in the Netherlands, that it has the classic making of a bubble, right? At some point, that could very easily pop. So, not sure it's the wisest thing to speculate on. And then the other thing about blockchains, I'm saying for like the third or fourth time now, is they're just slow. You know, tens of minutes to acknowledge any transactions. All right. Sorry about the interruption. I'll have to glue these videos together for YouTube probably. But I'm gonna go through all the comments and see if there are any questions and see what I have to recover. And if you've got new ones, Get them in there now, and I'll get to them when I get to the bottom of that chat scrolling. All right. This is a great pitch for QLDB. Well, I wasn't pitching for QLDB, but I do. QLDB is our database where it's constructed as a ledger, and so you get this cryptographic immutable, cryptographic proof of everything that's entered on that that ledger, which is pretty cool, and lets you detect any tampering or anything like that, which is nice. Is there a difference between chain replication and synchronous replication? Yes, definitely. Chain replication is a type of synchronous replication. It may or may not even be the most common. It's definitely a very simple kind, which is why I used it here for explaining. But most synchronous replication probably uses 2 or 3 phase commit protocols, where the primary is sending a proposal to the secondary. The secondary says, "Yep, I've definitely recorded it." Goes back to the primary. The primary says, "Yep, so I've definitely recorded it, and we're all good." That includes acknowledgements, which chain replication does not need to. So that's one difference. But chain replication is a type of synchronous replication. Let's see. Oh, there's some discussion of the math on how many atoms are in the universe. Only 10 to the 80 atoms in the universe. It's a very cryptographically low number. We would not be happy with that number for something like a key stream or something, or a random number generator. It's fascinating. Is the ledger agreed upon by all parties or something? What makes it authoritative? So yeah, I mean, that question came, I think, before I explained any of that. But yes, I mean, the idea here is the proposed transactions go into the blockchain network, and every node tries to win the race to record that series of pending transactions in the next block. And once they propose a winning block, everybody can verify that it's a winning block, and everybody can record it. And the second the majority agree that is the winning block, that's the winning block. That's the new ledger. And sometimes you can have forks in blockchains due to network partitions, where maybe these nodes become invisible to these other nodes, and these nodes go off and elect a winning block, and these nodes go off and elect a different winning block. And then when the partition resolves and everybody can see one another again, the minority kind of realizes, oh, we're screwed. We have to throw away all those things. They weren't winners. So that's why it's important not to have those kind of partitions. Sometimes those partitions happen because there's literally country level outages. Like if China is disconnected from the rest of the world, there's a significant enough percentage of the blockchain in China, right, that's actually a problem, right? That can happen. But it's been pretty rare, but definitely something you have to think about. All right, we've got some more here. Is there any way a ledger could be recovered if someone were to be able to compromise the consensus protocol by gaining 51% of the network? I mean, everyone would have to agree to start over and erase those transactions. So it would be a pretty big lift. I mean, that's one of the downsides of peer-to-peer systems in general. If you want to go change anything, you got to go convince everybody, or at least a clear majority, to go back and do it, which is hard. That's just like the forking problem we just mentioned. Cool. Some comments on the proof of work stuff. Pretty straightforward. Getting to the part where the stream disappeared. Sorry about that. Suggestions to reclassify the stream, which I think is a good idea. As a developer, is it worth it to learn the blockchain? I actually think it is worth learning how blockchains work inside out. They're pretty cool. You'll learn a lot about distributed systems and cryptography, both of which are highly in-demand fields. They're actually, a pretty good introduction to both of those areas. So that's a good reason to. And I mean, there's also clearly a lot of active blockchain development at the moment. I'm sure it's also a lucrative career field at the moment. We'll see if that sustains. Cool. Oh, Merkle trees. Oh my God. I see. Yeah, Merkle trees are like these chains of hashes, except they're trees, and they're ways to summarize data. You know, like if well, I'll cover a simple example. Why not? Since Matt mentioned it. If you've ever used rsync, right? You've used a Merkle tree as well. Rsync is this cool Unix utility for synchronizing two files. So, you know, it's kind of like SCP or a copy, right? It's for like copying one file from A to B. Except if you make a small change in A, it can very efficiently make the same small change in B. It doesn't have to just copy the whole file over again, right? And the way it does that is it oh, that pen's gone. Is like it takes the whole file and it splits it in two. Sorry, and it does a checksum of the whole file, say, right? And if the checksum on the whole file is the same, then nothing changed, so you don't have to do anything. But let's say the checksum is different. Okay, well now we got to find out where the difference is. So it then checksums the first half, right? And then the second half, and then sees, well, are there changes in either half? If there's changes if there's only changes in one half, then kind of zoom in and do the same again, right? And so on and so forth, all the way down until you get to wherever the smallest change is, right? And then only send that block over, right? So that's an example of a Merkle tree in action, where you've got this effectively tree of hashes, right? Like C1 is like the root in a tree where the left node is this hash, the right node is this hash, and so on and so forth. They're pretty intuitive. They're pretty funky things. All right. I think that might be all. As I said earlier, I'll probably do a separate stream someday on how like Paxos and Raft and distributed consensus protocols and so on, because that's interesting on its own. I might also do a Twitch stream someday on an alternative proof scheme, which doesn't waste CPU or memory, which is proof of physical distance, and to use the speed of light to try to form a network where you've got equal part close and remote participants, as an interesting way that's not so gameable because the speed of light can't be changed. But we'll see. I'm not sure what's coming up next week. And then, as I said right at the beginning of this talk, some of my Twitch streams have aged out on Twitch, and if you want to see them on YouTube, just go to my website, shufflesharding.com, and if you go to the videos page, there's a link right there for the YouTube channel, and they're all there. So you can, and this one will go on YouTube. I'll glue the two videos together if I have to for this, and that'll be that. Thanks everyone for joining. If you've got any other comments or suggestions or whatever, just send them at me on Twitter. It's probably the best place, and I'll try to get to them. Hopefully this was useful. All right.